Hello, in this lecture we'll be talking about models that contain both a factor covariate and a numeric covariate together. So our notation for the responses is going to be the same. We'll use lowercase y1 up to lowercase yn. Remember that this is just data, so this is something that's stored in the computer. We're going to have a single numeric covariate in these models. So we're going to label it just x1 up to xn since we don't need to distinguish between two different numeric covariates. And then we're going to have a single factor, and that factor will have j levels. And we'll use this indexing notation to tell us which level the ith observation has. So j of 1 tells us which of these capital J levels the first observation has. Okay, now let's jump into the model. I'm calling this the additive factor numeric model for response yi. I'll say what I mean by additive in a later page, but for now just take that to mean I'm doing the one factor model, b0 plus bji, and I'm adding the numeric covariate to it. So here it is. The model for the response is random variable capital yi, which is equal to b sub 0 plus b sub j of I plus c0 xi plus epsilon I. And the assumption about the epsilons is the same. So they're independent normals, mean zero, variance, sigma squared. So you'll notice that the just like in the simple linear regression, the numeric covariate gets multiplied by a parameter. Here I'm calling it c sub 0. It may seem a little bit strange that I'm calling this c sub 0 when we usually use the 0 subscript for an intercept, but that'll be clear once we move on to more complicated models why I'm doing that. All right, so the easiest way to kind of understand what the model is doing is to just pretend, make up some pretend data and then write down what the model is. So to that end, I'm going to suppose subject 7, so I equals 7, has level 3 of the factor. So in our notation, this just means that j of 7 equals 3. And if you plug this in down here, what you get is y sub 7 is b0 plus b3, because j of 7 is 3, plus c0 x7 plus epsilon 7. So if you'll notice from this equation, is it looks kind of like the simple linear regression. There's a part here that doesn't depend on x, so we're going to call this an intercept. And then there's a part here that's multiplied by x, so we're going to call c sub 0 a slope. And then, of course, there's the error. Just to do another example, suppose subject 5 has level 2 of the factor, so j of 5 is 2. Then we write out y5 equals b0 plus b2 plus c0 x5 plus epsilon 5. So again, this is going to be sort of just like simple linear regression. Here's the intercept, and then this c sub 0 is the slope. So what you kind of learn from this exercise is that the intercept, so we could think of this as the expected value of y, I, is a linear function of xi. And its intercept is b0 plus b sub j of I. In this case, it was b0 plus b3. And in this case, it was b0 plus b2. And in both cases, the slope is c0. If you notice from here, c0 and c0. So this is a case where we can think of this additive factor numeric model for yi. It's a model that's always a linear, whose expected value is a linear function of xi, but the intercepts depend on the level of the factors, but the slopes do not. There's a common slope. So just to say that in words again here, each level gets its very own intercept, but they must share a slope. So here's a sort of a picture of some fake data where I put x on the horizontal and y on the vertical. And then I've indicated the level of the factor with either a plus for level 1 or a circle for level 2. And what the model says is that the relationship between the expected value of capital Y and X is always linear. So within a level, so for level 1, this is the linear relationship, this gray line. And then within level 2, this is the linear relationship. You'll notice if I've drawn these well enough that the slopes are the same, which makes these lines parallel, but the intercepts are different. So the intercept for this one is b0 plus b2, and the intercept for this one is b0 plus b1. So keep in mind this kind of picture when you're thinking about the additive factor numeric model. Of course, sometimes there's going to be more than 2 levels of the factor. That just means there's going to be more than 2 lines, but they have to be parallel to each other in the additive model. So a note on degrees of freedom. The model degrees of freedom is going to be capital J plus 1. So let's think about why that is. The reason is written right above it. So each level gets its very own intercept. So if there's capital J levels, the model is going to contain capital J parameters just to describe the intercepts. But then there's a common slope. So you only need one additional number to specify the slopes because they're shared by all of the levels. So that means in total, the model is going to have capital J plus 1 model degrees of freedom. However, if you take all these parameters and count them up, you're going to get B0, B1, B2 up to B capital J. So that's J plus 1 parameters. Plus C0, the slope parameter, is going to give you capital J plus 2 parameters. So here's another case where the number of parameters, which is J plus 2, is larger than the model degrees of freedom. And our word for that is that this model is over-parameterized. Now, just like in the one-factor model, when we have an over-parameterized model, when we go to fit the model, we need to impose some kind of constraint. So this is a case where there's one extra parameter, so we need one constraint. Now, before we go into looking at a specific constraint, let's remember our anchor. So our anchor is that B0 plus Bj is always going to be the intercept for level J. If you remember back to the one-factor model, our anchor was that B0 plus Bj is the expected value for level J. Here in the factor numeric model, this is going to change. So our anchor is going to be B0 plus Bj is the intercept for level J. So it's the expected value when the numeric covariate is equal to 0. So just like before, different software packages will impose different constraints, but they all have this interpretation for B0 plus Bj. This will never change. So we'll just look at one of them, which is the R default. In R, the default is it sets B1 equal to 0. So it sets the intercept coefficient associated with the first level of the factor or the base level of the factor. It sets that equal to 0. Now, if you go through this exercise and try to isolate parameters, what you'll find is very similar to what we found for the one-factor model, but instead of the word expected value, we're going to use the word intercept. So B0, under the R default constraint, B0 is interpreted as the intercept for level 1, or the base level, and B sub j is the intercept for level j minus the intercept for level 1. So remember this when you're reading the output in R, that these parameters are interpreted as differences from the first level. Okay, now let's go back and let me fill in a detail about what I mean by this term additive model. And this is something that you should really pay very close attention to, because this is kind of central to one of the main things I want you to get from this course, is to understand what precisely is the distinction between an additive model and an interaction model. So let's define additive first. And to do that, we're going to need this term called effect. So I'm going to define this term. The effect of a covariate is the impact on the expected response when changing the covariate. Okay, so that's a bit of a word salad. So the effect of a covariate is the impact on the expected response when I change the covariate. So let's think about what this means in more specific cases. So when you have a numeric covariate, we can think of the effect of the numeric covariate as the slope parameter, because the slope parameter tells us how much the expected response will change per unit change in the numeric covariate. Okay, so that's kind of a little bit straightforward to understand, that when you have a numeric covariate and you change the numeric covariate, you expect the response to change according to what the slope is. So the number that multiplies that numeric covariate. For a factor covariate, it's slightly different. So we think of the effect of a factor covariate as the difference in expected response from one level to another. So the way we're going to talk about this is if you change the level from 1 to 2, how much do you expect the response to change? And that is what we're going to talk about as the effect of the factor. And of course, for a single factor, if there's 6 different levels, you're going to have many different effects associated with that factor. So you have an individual effect for each level of the factor. Okay, now we're prepared to say what we mean by additive. And I put this in a box because this is very important. A model with multiple covariates is additive if the effect of each covariate does not depend on the values of the other covariates. So this is one of these phrases I want you to just kind of memorize it, internalize this, and it will make more and more sense the more examples you see. So a model with multiple covariates is additive if the effect of each covariate does not depend on the values of the other covariates. So here's a picture. I've just copied this down here. And before we get into mathematical details, what I want you to do, or want to show you, is how this works in a picture. All right, so if we think about what's the effect on the expected response of changing the level from female to male. So if we sort of pick a value of the height at age 9 variable, which is the example I'm using here. So the expected response when height is this for a female is this value on the gray line right here. And then the effect of changing to male would be to increase the expected response by this amount, which is the difference between the two lines at this value of the covariate. Now, as a consequence of these lines being parallel, if I were to pick this value of the covariate and I move from this line to this line, it's exactly the same change. So what that means is that the effect of moving from female to male is the same no matter which value of the numeric covariate we have. And therefore, according to this definition, this is an additive model. Okay, so that's what I mean by additive. You can also do the reverse. So you can say, what's the effect of increasing the height at age 9 by 1? Well, it's going to go this way by 1 and up by 1, which is exactly the slope. So this is the effect for female of increasing height at age 9 by 1. And the effect for the male is exactly the same. You go over by this much and you go up by this much, which is the slope. Now, since the slopes are the same, the effects are the same, and therefore the effect of changing height by 1 does not depend on the level of the factor variable, and therefore it's an additive model. All right, now let's see how that works mathematically. And what I want to show you is why this form of the model has the property I kind of just described to you qualitatively. So here I've just written down the additive factor numeric model. So this is the same as before. And then I'm going to give you an example data set. So this is just data I made up for the purpose of illustrating the fact that this is an additive model. So there's 4 observations. What I've done with this data set is I have 2 female subjects, 2 male subjects. And height at age 9 is either 133 or 135. This is in centimeters. So I have all combinations of 133, 135, and female, male. And just so we know which levels we're talking about, I've coded female as 1, male as 2. This is in line with what R would do. R would do it alphabetically. So F comes before M. All right, so using this data set, we can illustrate a lot of things. So I'm going to go through 4 different comparisons. So the first one is I'm going to think about what is the effect of height at age 9 when sex equals female. So to do that, I'm going to look at these first 2 observations. So what's important about these first 2 observations is the sex is held constant at female, but height at age 9 increases by 2 from subject 1 to subject 2. So if we compare the expected values for these 2 observations, we're looking at the effect of height at age 9 when the sex is female. So let's do that. So I'm going to look at expected value y2 minus expected value y1. So expected value y2 is going to be b0 plus b1. It's a b1 because j of the second observation is 1 because the second observation is female, which has level 1. Plus c0 plus x2, that's just c0 xi. And then expected value y1 is b0. It's also b0 plus b1 because the level is female, which is the first level, plus c0 plus x1. Now if I take the difference, the b0 plus b1s cancel, and I get c0 times x2 minus x1. So what this means, and of course this quantity is 2. So x2 is 135, x1 is 133, so this is 2. I haven't written that out, but this is equal to 2. So it's going to be c0 times 2. So the effect of increasing height at age 9 by 2 when sex is female is c0 times the difference in the x's. Now let's repeat the same thing, but we're going to say the sex is male. And to see that comparison, it's observations 3 and 4. So these 2 are both male, and height at age 9 increases by 2. If you go through this calculation for expected value y4 minus expected value y3, you get b0 plus b2 because the level is 2 plus c0 x4 minus b0 plus b2 because the level is 2 here as well plus c0 times x3. And so things will cancel and you get c0 times x4 minus x3. And again, this is 2 as well, so this is really 2 times c0. And what you see by comparing these two is that the effect of increasing height at age 9 by 2 when sex is female is 2c0. And the effect of increasing height at age 9 by 2 when sex is male is also 2 times c0, which means that the effect of height at age 9 does not depend on the level of the factor. So that's our first clue that this is an additive model, and this is how it works out in math. Of course, we can go the opposite direction, and we can look at the effect of sex when we hold the height constant at one value versus holding it constant at a different value. So I won't go through all the details here, but you can see the effect of sex when height at age 9 is 133. The right comparison is going to be observations 1 and 3. So these both have height at age 9 equal to 133, but the sex changes from female to male. So if you look at the difference in these expected values, you get b2 minus b1. The reason is that the b0s will cancel, and this term c0x3 will cancel with c0x1 because x3 is equal to x1. So the height at age 9 is 133 here, and it's also 133 here. So those will cancel, and you're left with b2 minus b1. Now, if you want to compare the effect of sex when height at age 9 is 135, you're going to need to compare observations 2 and 4. So here they're both 135, but the sex is different. So if you go through that calculation, b0s cancel, and also the c0 times xi's cancel because x4 is equal to x2. These are both 135. And you're left with b2 minus b1. So what this means is that the effect of sex is always b2 minus b1. It does not depend on the height at age 9. Okay, so the comparison between these two, this is like looking at what is the difference between the two lines. It's always the same. It's always this amount. And by comparing these two, this is like comparing the slopes. The slopes do not depend on the level of the factor. All right, so those were additive models, and those are really useful. And we should remember when we're working with an additive model, we're making a specific assumption that the effect of each variable does not depend on the values of the other variables. Now that sometimes we won't want to make that assumption, so we need an alternative. We need non-additive models. And non-additive models, we can also say, are called interaction models. So you've probably seen interaction models before, but maybe not explained in this particular context as sort of the opposite of an additive model. All right, so let me give you, so this I'm calling the factor numeric interaction model. And it's going to be very similar to the factor numeric additive model. The only difference is that instead of C0 times xi, it's going to be C0 plus C sub j of I times xi. So now you see why I use C0, because I'm going to have additional parameters C1 up through C capital J, which serve to change the slopes. Okay, so if you stare at this equation, what you learn is that the expected value of yi is still going to be a linear function of the numeric covariate. So you're going to have a part here, b0 plus b sub j of I, which is not multiplied by x, so we can think of this as an intercept. And then we have a part here, which is multiplied by xi, so we can think of this as a slope. So it's still, we think of it as a linear function of xi. The expected value is a linear function of xi. And we have a different intercept for each level. So for the jth level, it's going to be b0 plus bj. We also have a different slope for each level. So the slope is going to be c0 plus c sub j. So this is different from the additive model in that the slopes are allowed to be different for each level. So we're going to talk below about constraints. It's going to be over-parameterized. But this is going to be your anchor for the non-additive or interaction model, that b0 plus bj is always the intercept for level j, and c0 plus cj is always the slope for level j. This won't change. Okay, so again, let's plug in some numbers just so we can get a feel for what this model is doing. So suppose subject 7 has factor level 3. So you'll get b0 plus b3 plus c0 plus c3 times x7 plus error. So now you should be more clear that this is an intercept. This is the expected value if x7 were 0. And this part is the slope. This is the amount that the expected value increases per increase in x. Just to do another one, suppose subject 5 has factor level 2. You'll get b0 plus b2 plus c0 plus c2 times x5 plus epsilon 5. So here now, instead of b0 plus b3, the intercept is b0 plus b2. And instead of c0 plus c3, the slope is c0 plus c2. So both the intercept and the slope changes. All right. So that's how it works in an example. I encourage you, if I write down a complicated model like this, to try to just plug in some numbers and make sure you understand what this works in how this works in specific cases. Now let's think about the model degrees of freedom. Forget about the parameter for a second. All this model says is that the expected value is a linear function of xi, and each level of the factor gets its own line, meaning that it gets its own intercept and its own slope, and there's no constraints that the slopes have to be equal for each level of the factor. So they're going to be capital J intercepts and capital J slopes needed to specify the model, which means the model degrees of freedom is 2 times capital J. Okay, so we can figure out what the model degrees of freedom without, thinking about the mathematical representation of the model, just thinking of it as it's a model that's linear as a function of the numeric covariate, and each level gets its own line. Now this model is overparameterized because if you count up all the parameters, there's going to be 2j plus 2 parameters. So here's a case where we have 2 additional parameters over the model degrees of freedom, and this means we're going to need 2 constraints. So to make sure this isn't too confusing, we need 2 constraints, so we need to specify it with 2 equal signs. What I'm giving here are 2 separate constraints. So these are 2 separate ways of doing it. So what I mean by that is that this is one set of 2 constraints that could be used. This is a separate set of 2 constraints that could be used. So let's do this one first. So this is 2 constraints, so this is going to be good. So these constraints say that B0 is 0 and C0 is, I don't know why I wrote 2, that's a typo. C0 is 0. And if you impose this constraint that both C0 and B0 are 0, then the interpretation of B sub j is just the intercept for level j, and the interpretation of C sub j is the slope for level j. So this one's kind of simple. It just means that bj is the intercept level j, cj is slope for level j. Now the default in R is something different. So this is a separate constraint. Of course, you need 2 constraints. And in R, the default is going to be to set B1 to 0 and C1 to 0. So what's going to happen is it's going to leave in these B0 parameters, going to call that the intercept. This is the intercept for level 1 of the factor. And then it's going to have another line which doesn't contain, it's going to just have information about the numeric covariate and not any information about the level. So that's going to be C0. That is the slope for level 1 of the factor. And then it'll contain additional lines, and one of them, each of them will correspond to B2 up to B capital J or C2 up to C capital J. And B sub j is the intercept for level j minus the intercept for level 1. And C sub j is the slope for level j minus the slope for level 1. So these additional parameters are interpreted as either a difference in intercepts or a difference in slopes from the first level. Okay, I fixed my typo here. This is, again, C0 equals 0. All right, so let's see why this model is not additive. And let's go back to our example data set. So if we wanted to look at the effect of height at age 9 when sex is female, we needed to compare the second and the first observations. So if we write out what the expected values are, this is the same as before, but of course we're going to add C1 to the slope. And this is the same as before, but sex is female, so again it's C1 to the slope. And if you take the difference between these two, you're going to get, the b's are going to cancel. You get C0 plus C1 times the difference in the numeric covariate. In this case, the difference in the numeric covariate was 2. It was 135 minus 133. So this is the effect of height when sex is female. C0 plus C1 times 2. Now, if we want to look at the effect of height when the sex is male, we needed to compare observations 4 and 3. And if you write out the expected values, it's going to be this. This is the expected value for the 4th observation. Remember, it has level 2 of the factor. This is the expected value for the 3rd observation. It also has level 2 of the factor. And things will cancel, and you'll get C0 plus C2 times the difference in heights, which was 2. So this is the effect of changing height from 133 to 135 when the sex is male. And now you'll see that these two are different. So for the females, it was C0 plus C1 times 2, whereas for the male, it's C0 plus C2 times 2. So our conclusion is that the effect of changing height depends on the level of the sex factor. So that makes it a non-additive model, which we call an interaction model. Now we can do the same exercise for changing the sex for two different values of the numeric covariate. I'll skip the computation and just get to the punchline here, is that to compare the effect of sex when height at age 9 is 133, you'll compare observations 3 and 1. And this is what you get. You get B2 minus B1 plus C2 minus C1 times 133. And then for comparing the effect of sex when height at age 9 is 135, you'll compare observations 4 and 2. You get B2 minus B1 plus C2 minus C1 times 135. So this part is the same, B2 minus B1, and this part is the same, C2 minus C1, but here it gets multiplied by 133, and here it gets multiplied by 135. So these are indeed different. So our conclusion is that the effect of sex when height is 133 is different from the effect of sex when height is 135, and therefore it's an interaction model. Okay, so this is just reiterating that point. Okay, so what I want you to remember is that when we talk about interaction models, what we're really saying or specifying in the model is that the effect of one variable depends on the value of the other variable. And this is the most straightforward and correct way to understand interactions. When you put an interaction in the model, you often say you're kind of like multiplying covariates together. And that is true. That's exactly what you're doing. But in terms of a real interpretation for what that means, this is what it means. The effect of one variable depends on the value of the other variable. Okay, so we haven't talked about testing. So something to discuss in office hour is how would we test for an interaction in this height sex model. And then in general, we'll need an F-test to compare the interaction model to the additive model. And what will the numerator degrees of freedom be in that F-test?